Okay, in our last episode, we looked at confidence intervals for the mean, but we looked at them when sigma was known, the population standard deviation was known. And so what we did was we ended up using the normal distribution. Okay, so in other words, we used z values, and in particular, we used critical z values there. So a good question is, what do we do if we don't know sigma, which is often the case? We don't know the population standard deviation, and we have to use something else. So in the case where sigma is unknown, we have to use a different distribution. We're going to use the t distribution. So let's take a look at what that would mean. So the t distribution. All right, so we're going to be using this, and the first is the key there, when the population standard deviation is unknown. Sigma is unknown. Now, essentially we're going to be using this when the sample size is less than 30 and the random variable x is normally distributed, or approximately normally distributed. So our population is at least approximately normally distributed. Now, we could use it for sample sizes of more than 30, but in that case, we would most likely just use the normal distribution instead, the z values instead of the t distribution. So this is when we're really going to be using it. The key is when the sigma is unknown. Okay, so the t distribution, what does it look like? How do we get t? Well, it looks a lot like the calculation of z, except for the fact that we are going to use the sample standard deviation, s, instead of sigma. Okay, so that's the difference right there. And that will make a bit of a difference in how this distribution looks. So now critical values of t are denoted by tc now instead of zc. Let's go a little further in looking at the t distribution. So what are some properties? Well, the mean, median, mode of the t distribution are all equal to 0. All right, well that's just like the normal distribution. The t distribution is bell-shaped and symmetric about the mean. That's also just about like the normal. Total area under a t-curve is 1. That's like the normal. All right, so here's where we get some differences. The tails in the t distribution are thicker than those in the standard normal distribution. We'll see on the graph in a minute. The standard deviation of the t distribution varies with the sample size, but is greater than 1. Okay, so that is something that we'll see how that impacts going forward. All right, what else? So that when we say the t distribution, we're actually talking about not one specific curve, but a whole family of curves, depending on the degrees of freedom. So the degrees of freedom are the number of free choices left after a sample statistic such as x bar is calculated. So the way to get that, the degrees of freedom, is we're just going to take the sample size minus 1. Essentially, we've lost 1 degree of freedom in making our calculation of the sample statistic, and that's why n minus 1 there. So that's what we have to remember, is that the degrees of freedom is always 1 less than the sample size. Okay, so a little more, let's look at the curves. As the degrees of freedom increase, the t distribution approaches the normal distribution. All right, so if we look at these curves here, we'll see that this bluish one here is the standard normal, and the other curves here are different t distributions for different degrees of freedom. So you see that the one here with the degree of freedom of 2 has a very thick tail. So this is what we're talking about as having a thicker tail than the normal. But you see that as you increase the degrees of freedom, the t-distribution curve gets closer and closer to the standard normal curve. So that's why if you get to about 30 or more, then there's really very little difference between the t-distribution and the standard normal. So let's look at how we would actually get values out of the t-distribution. Okay, so one way would be to go back to a chart like we've looked at before, and we'll use this basically to illustrate the idea, and then we're going to use Excel to look up values. Okay, so the first thing we're doing is confidence intervals, so we're going to focus on the level of confidence C. All right, so the idea is that here we have different columns for different levels of confidence, from 80% all the way up to 99%. And then what's different here is that we have to actually factor in the degrees of freedom here. So there isn't one value, t-value associated with a level of confidence like in Z. There are lots of them depending on how many degrees of freedom. So we have to match up the confidence level and the degrees of freedom. So let's look at an example. All right, find the critical value TC for a 95% confidence level when the sample size is 15. Okay, so we have our confidence level, C equals 0.95. And we have our sample size, little n is 15. So automatically I know the degrees of freedom is n minus 1, so that's 14. All right, remember, 1 less than the sample size. All right, so then we would go into the chart. There's our 95% confidence level. There's our 14 degrees of freedom. And again, we follow down in there, and we would get 2.145 as our TC value. So that's how we could do it with the chart. Of course, we're not going to want to use a chart. We're going to want to use some technology here. So if I'm going to bring up now the normal and t-distribution in Excel file that I have available for you here. I'm going to see that we can easily do this sort of thing with Excel. So the first thing we're going to be looking at is this, using the inverse t distribution, two-tailed, to give us t-values. In this case, we're going to be looking to get critical t-values. All right, so realize that when we do this, we're going to be specifying the probability and the degrees of freedom, all right, because both of those are important in getting a t-value. Okay, but here is the big difference. When we're using the Excel, this probability is not going to be the confidence level. It's going to be what's left in the tails. So if we were doing 95% confidence, that means that we would be doing a 0.05 or 5% left in the tails, and that's the probability there. All right, so let me go back to the notes here. So in this case, where we were using the 0.95, we are actually going to be using the two-tail version, so 0.05. So talking about 95% level of confidence and talking about 5% in the two tails is the same thing. And this is what we're going to use when we go to Excel. So let me bring up Excel here, and all I would do is equals, and if I start with T, then I can see that I have a lot of options, and so I want the T inverse two-tail version. I want the probability, if we're going to redo the one we did, 0.05, so that's 5% left in the tails, and then 14 as the degrees of freedom, and there we go. There is the 2.145 that we saw in the chart approach. So that's our easiest way to really go about getting critical t values at this point.